let me introduce Dr. Ravi Sundaram. He is Director Sanjay Geotechnical Private Limited (FIGS), Fellow of Institution of Indian Geotechnical Society. Is a practicing geotechnical engineer with 44 years of experience. His expertise includes geotechnical and geophysical investigations, ground improvement, piling, foundation strengthening, load test, and so on. I think you have a very wide spectrum uh, dealing with geotechnical engineering. So his expertise include advanced testing technologies such as electric cone penetration test, SPT, energy measurements, geophysical test, dynamic pile load test, and so on. His interests include liquefaction, expensive soils, soft clays, artisan condition, and he has been involved in developing solutions to geotechnical problems for residential and commercial projects, tall buildings, thermal and solar power plants, wind turbines, industrial structures, refineries, and it goes on. So he has published more than 75 manuscripts reflecting his experience in geotechnical practices. He was awarded IGS Delhi Chapter Lifetime Achievement Award in the year 2012 and then IGS Dinesh Mohan Award for Excellence in Professional Practices in 2018. He delivered the 6th Madhav Lecture 2017 on geotechnical investigations in difficult ground condition, and he has delivered keynote lectures in Indian Geotechnical Conference and other forums. He was chairman of IGS Delhi chapter in IGS EC member for 2 terms, and he is member of several BIS and IRC code committees. He was active in organizing 13th International Conference on Soil Mechanics and Geotechnical Engineering, then 6th ICEG, IGC 2012, DFI 2014, and ISGTI 2018. He strives to integrate field practice with academic research to be responsive to complex geotechnical challenges facing our country. So, with this brief introduction, Dr. Ravi Sundaram sir, I would like to invite you for your keynote address on the topic Advanced Geotechnical Investigation Technologies to Optimize Foundation Design of Tall Buildings. Over to you, sir.
Thank you very much. I'm really grateful to you for that very kind introduction. I will be talking about advanced geotechnical characterizations and particularly for tall buildings, how you can optimize the foundation design, the foundation costs, and make sure that a good geotechnical investigation results in substantial saving for tall buildings. By tall buildings, we are meaning 100, 50 meters or more, and maybe up to 150, 200-meter tall buildings. So in the recent years, there has been a lot of very significant advancements in geotechnical investigation and testing methods. There has been a shift from the traditional methods of investigation using boreholes and conventional SPTs to more modern investigative methods in so that in housing and industrial projects, this has really revolutionized the foundation design. Now, these techniques, which I'm talking about, one is electric cone penetration test with pore water pressure measurements, SPT energy measurements. So if you were to measure the energy being transferred to the SPT anvil, you can standardize it to a 60% energy transfer. So you will normalize the SPT measurement so that the quality and consistency of the SPT improves. Other tests like pressure meter tests, geophysical tests, cross-hole seismic test, seismic cone, and various other tests have been very effective for site characterization and to identify the subsurface conditions. This has marked a paradigm shift in the foundation analysis. The impact of using these tests is that now you can classify the soils effectively, evaluate more realistic values of in situ bulk density, shear strength, deformation characteristics, stress strain characteristics, also the hydraulic parameter. So using these parameters, a more reliable assessment of the foundation behavior, talking about net bearing pressures, pile capacities, liquefaction susceptibility um, of the soils. So you can make a much better assessment. So if you will compare it with the conventional methods, what SBC you would have conventionally assessed from the normal investigation, there can be a substantial increase. So this can result in uh, cost savings for foundation construction. And here I'm going to emphasize in this presentation on tall buildings, 50 to 150-meter high, also heavily loaded commercial buildings, industrial facilities, etc. And obviously, a more economical foundation reduces the carbon footprint, minimizes the emission of greenhouse gases. So it's a win-win situation. So in this presentation, I'm going to present two case studies, field data of CPT pressure meter from two tall buildings in Gurgaon. The CPT helps to evaluate the various soil properties, engineering properties, keeping in mind the genesis of the soil. It demonstrates the consistency of the data. A comparison with the SPT N60. N60 is 60% energy transfer. And determination of various geotechnical parameters commonly using the commonly used correlations. So these case studies demonstrate that higher safe bearing capacities and pile capacities can be justified from the CPTU-based analysis, resulting in substantial savings in the foundation costs. So that's the typical CPTU equipment for pore pressure measurement, cone-tip resistance, friction resistance, and so it could be mounted on a crawler in this, or it could be, um, you know, you can use anchors to hold down the rig and perform the test. So this is the typical piezo cone, and the pore pressure sensor at just above the cone is called the U2 position. This is the most commonly used scheme. So let's see what are the advantages of CPT. Number one is the speed. So it's much faster than a conventional drilling and sampling using boreholes. So you could probably do 2 to even 3 tests a day to 30-meter depth using the CPT, whereas one borehole would usually to 30 to 40-meter depth would take 2 days. You get a continuous profile, a near continuous record of the subsurface conditions, and clays, sands, gravels. All these provide uniquely distinct results, which can be help to identify the soil classification. It is feasible to identify thin zones of soil, which might otherwise be missed out using drilling and sampling methods. Because there is an increased productivity, there less time to complete each point. So within the same time, you can investigate more number of points and also get more data than what you would conventionally do from a drilling and a sampling operation. It allows for adjustments in scope without loss of time for the overall project. Economics, obviously, you're saving a lot of money by getting more data at lesser cost and lesser time for investigation because the test is rapid. And so it also provides the opportunity to review the results in timely fashion. If any remedial measures are to be taken, quickly decisions can be taken. So you have a large volume of data that helps you to get better quality data. Then we talk about soils which are difficult to sample, like soft clays, loose sands. You cannot get undisturbed samples in these type of soils easily, so you can get the properties very reliably. There's minimum disturbance to the surface since there is no borehole. No, the cleanup and surface restoration required is minimal. No cuttings or drill cuttings are generated for removal or disposal. And the biggest advantage, of course, is the higher bearing capacity and pile capacities. So for a specified value of permissible settlement, you can justify higher net bearing pressures. Similarly, higher pile capacities. So you can economize your design. Of course, every test has its limitations. No sample is obtained. That is a problem which many engineers are not very comfortable with. To overcome this, an attachment to collect disturbed samples has been developed. So with the CPT pusher, you can push the sampler to different depths and collect some samples. So this can help you in getting the soil classification. You can actually see the soil and make sure that you've got the right type of soil. So overall, my advice is that you should use a combination of boreholes and CPTU for a better assessment. Slightly more complex than the conventional borehole. So it requires more attention to the initial setup. There are a lot of small mechanical and electrical details which have to be taken care of. Requires a portable computer and a data acquisition system. So a technician familiar with handling the electronics and digital data collection is required. Of course, the current generation is usually comfortable with computers. A piezo cone requires careful deep airing before conducting each test. So you would have to de-air your cone before doing the test. Uh, uh, Availability is an issue. Very few companies in the country have the test. But the availability is growing, and very soon there should be quite a few companies worldwide having the right kind of equipment. Also, limited calibration facilities available, so that is a matter of concern. Again, we hope that the calibration facilities will increase. Rock formations and strata containing boulders, the test has a limited application because you will not be able to push the cone through hard rock or boulder strata. So I start with two case studies, which will be actually the purpose is to demonstrate the benefits of CPTU and pressure meter in design of foundations. A comparison of soil parameters from conventional analysis to those from advanced testing methods illustrates the superior quality of data, increase in safe bearing capacity of isolated foundations and raft foundations, pile capacities, etc. This can be substantial. The saving can be more than 50 to 80% in cases even more. So the first case study, this is a multi-story tower block in Gurgaon. This plot area about 8.9 acres. So 5 high-end towers of 40 story, 2 towers 30 story, and all these have 3 basements. This also includes a commercial building and economically weak building for economically weaker sections, sports facilities, club, etc. So the scope of the geotechnical investigation here, 5 boreholes to 60-meter depth, 3 boreholes to 30-meter depth. 4 SPT analyzer tests to measure the SPT energy transfer, 15 electric cone penetration tests, pressure meter tests in 5 boreholes, and 2 cross-hole seismic tests. So geophysical test was also performed at this location. So that's the layout of the towers and the layout of the geotechnical investigation at this site. So now this is the borehole profiles. So these are typical few boreholes which are down to 60 meters. And also I have a selected few boreholes, the CPTs, and the strata which we interpreted from the CPT. So this is being illustrated here to show that we can actually determine what the strata is, and also there are correlations to assess from the cone tip resistance what the equivalent N value is. So this site is in the Indo-Gangetic alluvium. The deposits primarily consist of sandy silt of low plasticity with some intermediate silty sand zones. The soil strata and SPT values are also interpreted from the CPT. The groundwater was shallow at 3.3 to 5.9 meter depth. So all these SPT values are corrected for energy transfer in the boreholes, whatever the actual SPT values were measured. These numbers are showing these are corrected for energy transfer, to standardized to 60% energy transfer. So this is the way the SPT energy measurement record looks like. So at different depths, if you can see here, 13.1, 14.5, 15.7 meter depths, the SPT was measured, and the energy transfer has been measured for each blow, and then an average value with standard deviation has been determined. Overall average value here was 73.5. So since we used 4 rigs here, so all of them were actually monitored. So for the four rigs, these were the SPT. These are the 4 rigs, and the energy transfer ratio, roughly 73 to 75%. So these are the SPT field N values corrected for energy, and the combined plot of all the SPT values. You can see the trend is fairly reasonable. This is the CPTU test in progress. You can, and this is the data acquisition being done here, and you can see the graphs which are generated by the system. So from the various CPT tests, an average profile was developed. So this shows me the cone tip resistance, sleeve friction, pore water pressure, and friction ratio versus depth, and the interpreted soil type here. Basically, Robertson's correlations are used to assess the soil type. So from this, we have interpreted the values of SPT N value, shear strength of soil, undrained shear strength, friction angle in the sand layers, and also the density values. So you can, here you can see the borehole SPT values measured in the boreholes. This had been overlaid on this graph, and you can see there is a very good match here. Similarly, the undrained shear strength values from laboratory tests, you can see a fairly good match. The bulk density values, and these are the data from the undisturbed samples. Because of sample disturbance, they're showing slightly lower densities. But overall, there is a very good match with the borehole data. Other parameters, constraint modulus. The inverse of the constraint modulus is the MV value for consolidation analysis. The E value, Young's modulus, over consolidation ratio, all these parameters can be determined. Also, the shear wave velocity can be assessed from the CPT data. And when we did the cross-hole test results, the shear wave velocity, which was actually measured from the cross-hole test result, you can see a very good match. So this is the geotechnical design profile developed from the CPT. These are the various layers which have been identified and the various soil properties. So this shows the pressure meter test in progress at the site. So this is the control panel of the pressure meter. A typical pressure meter test results, pressure versus volume. The field curve has been corrected for stiffness of the membrane itself and the stiffness of the hoses. So this straight line portion of the pseudo-elastic curve, this is a function of the deformation modulus. And this maximum value, this is called the limit pressure. So these are the parameters determined from the pressure meter test. So I have the limit pressure versus depth and the deformation modulus. This is a volumetric deformation modulus in the pressure meter. Also, you can determine the horizontal stress from the pressure meter, in which you would plot the creep volume versus the pressure. And so this is the horizontal stress from the pressure meter. And we did a plot of the pressure meter parameters, that is the K0, assuming where K0 is equal to 0.55, and then what the pressure meter predicted slightly higher values of horizontal stress. So these parameters are used for design of the retention system and the diaphragm wall. So this shows the cross-hole seismic test in progress. So 3 boreholes have been drilled in a straight line, and this is the pressure, the geophone being inserted into the borehole. This is a data acquisition system. So the shear wave velocity, and this is the shear wave velocity, and this is the compression wave velocity versus depth. And then you have the dynamic Young's modulus and the dynamic shear modulus. The modulus of elasticity has also been determined from various correlations. There are SPT-based correlations, there are CPT-based correlations, also cross-hole seismic based correlations, and also the pressure meter. So based on all these tests, now we have such a wide scatter of the E-values. So then we have to pick up a reliable design profile closer to the CPT and the pressure meter to get the design value. So let us see what is the increase in modulus of elasticity using advanced testing. So at shallow depths, it may be a little less, but as you go, you have more than 50% increase in the E value when you use advanced testing methods. So that obviously results in lower settlements. So we did the bearing capacity analysis for isolated and rough foundations and rough foundations at 12, 14, and 16 meter depth. This was required because the client was considering making 3 to 4 basements. So we did the analysis for different methods. So this is the bearing capacity tier criteria. So this is the IS criteria. This is the Robertson analysis, and this is the pressure meter analysis. So if you will look at the values, you can see there is an increase in the bearing capacity of up to 54%. And also, as you go deeper for different sizes, substantially. Now, this is the settlement analysis. So the analysis at 12, 14, and 16 meters for an isolated foundation of 3-meter width and a raft foundation of 20-meter width. Again, you can see that by using advanced techniques, the net allowable bearing pressure, even for a 50-millimeter settlement, has increased substantially. As you know, for raft foundations, your permissible settlement now has increased substantially in the code to 75 to 125 mm. So obviously, these values will go up. So this is the bar chart showing the SP shear criteria and the settlement criteria, how much advantage you can get from the use of advanced testing methods. So you effectively, if you were to plot versus depth, the increase in allowable bearing pressure, so there is more than 60% to up to 128% increase in the values. So you can see that this kind of an increase obviously results in huge economy. Analysis was also done for pile foundations. This analysis here shows the pile cutoff level at 12 meters. So from basic testing to advanced methods, if I were to look at the average numbers here, there is again more than 70% increase in the pile capacity for pile lengths of 26 to 32 meter length. 1000 mm diameter. Again, this shows me a bar chart of the increase in the pile capacities from the different methods. So I get a 70 to 85% in the theoretical pile capacities. Obviously, this would have to be proved out by laboratory testing, pile load testing, so that you actually know how much capacity you can stretch your pile. The conventional approach has been that as long as my safe capacity theoretically calculated is lesser, and the you can see that the load test is showing me that the pile is settling very small amount at that stage. So there is a obviously margin to increase. So there's a theoretical basis to justify the higher capacity. So all this transfers into money saved. And if we were to do a basic testing, you would have had to go for piles. If I go for a 28-meter long pile, I have a saving of more than 21 crores here. Whereas if I were to go for advanced testing, I saved quite a bit on the foundation cost. But because of uplift, because the groundwater is shallow, some anchors were required. About 4 crores were required for the anchors. So the difference would have to be considered as the actual cost. So, and the cost of the advanced testing about 45 lakhs. So if you were to look at the net saving, the return on investment is more than 3,600%. It's a huge saving. Plus, in addition to the saving in the foundation cost, there is a saving in the construction time. So you saved about 2-3 months because you didn't need the piles. There is a risk mitigation because you know that you are doing it right. Again, reduce carbon footprint, indirect savings, overheads, etc. So we're talking of huge savings which can be achieved by doing these tests. I move on to the second case study. This is also in Gurgaon. This is a premium housing complex having 7 towers. ground plus 32 floors, 2 basements. The towers, the height of the towers is about 117 meters. So that's an architect's visualization of how it's going to look like. The basement floor depth of 8.4 meter below the finished ground. So the scope of investigation here, 13 boreholes to 40-meter depth. Again, SPT and energy analyzer, SPT analyzer to measure the energy transfer. 36 electric cone penetration tests. So what was done is economized by, instead of doing more boreholes, some of these were converted to electric cone penetration tests. In addition, 2 footing load tests were performed on a 1.5 into 1.5 meter size concrete footing at the planned foundation level after excavation. So that's the layout plan of the various structures. That's the investigation in progress, the CPT test being done, the data acquisition from the CPT. So in this data, in this presentation here, I am just taking this portion of the site. We have got 2 boreholes here and 1, 2, 5 CPTs. So these are the 2 towers here in this area, which I'm comparing just to see what the overall assessment is. So again, here I have the boreholes and the strata interpreted from the CPT. So again, I have silty sand in the top, below which I have sandy silt of low plasticity. Groundwater was there, 7.5 to 8.8 meter depth. This is the CPT results, the average profile, cone resistance, leaf friction, pore water pressure, and then the friction ratio. This is the soil behavior type. This is the soil classification, which is interpreted from the CPT. Again, the SPT values have been overlaid on the CPT for a comparison. The shear strength, whatever was determined from the laboratory tests, the friction angles, the bulk density values. Here, these bulk densities were somewhat lower, but overall reasonable match. Again, constraint modulus, Young's modulus, over consolidation ratio, all these parameters have been determined. This is the footing load test being done using a truss. 16 anchor piles were used for the footing load test. Dewatering was done to lower the groundwater level 1 meter below the footing level. This is the close-up view of the hydraulic jacks. So this truss is capable of supporting load of up to 600 tons. These 600 mm diameter both piles were used as anchors. These were extending to 13-meter depth. The top 4 meter was filled with sand, compacted to approximately the same density as the surrounding soils, so that it does not influence the pile settlement. The concrete was below 4 meters. Each reaction pile was designed to withstand a pull-out load of about 34 tons. The reinforcement of the piles was welded over the girders placed on the truss so that the reaction piles are in tension when the footing is loaded. So maximum test load was about 450 tons. This was applied in 10 equal increments. So each load was held until the rate of settlement was less than 0.02 mm per minute. Maximum load was held for 24 hours, and then it was unloaded. So dewatering, of course, as I told you, has been done. So this is the results of the footing load test. The test was carried out up to failure, and from the results, we interpreted the bearing capacity, ultimate bearing capacity as 1090 kPa. So maximum measured settlement at the ultimate bearing pressure was 13 mm. So we also determined the modulus of subgrade reaction and the E values. So this is the design profile developed based on the boreholes and CPT. So the settlement analysis was done by different methods. The classical analysis, considering the total settlement equal to immediate settlement plus consolidation settlement. So we did two types of analysis. One using the conventional analysis using the borehole data only, and also the second analysis using the enhanced parameters from CPT and pressure meter. The CPT-based analysis is as per IS code. The also done by using the method proposed by Robertson and Cabot. Also, the footing load test was extrapolated. So we took three cases: 1.5 meter, 10 meter, and 20 meter wide square footings, varying at 8.5 meters depth, to compute the settlement under the applied bearing pressures 250, 400, and 500 kPa. So if you will look at these results here, for a 1.5 meter, actually the footing was also 1.5 meter wide. So these values are actual measured settlements. And if you were to compare them, there is a very good match with the parameters interpreted from the enhanced parameters, whereas the conventional would give you much higher settlements. The Robertson-based analysis also gives me a very good match. The IS code has a reasonable match, but still it's not as good as what is predicted by Robertson. Similarly, for the 10 meter wide foundation, you can see that the match again for the enhanced parameters is good, and also from the Robertson analysis. Extrapolation from the footing load test. Of course, when you cannot, if you were to extrapolate for a 20 meter wide foundation, it may not give you very good extrapolations because it does not model the soil at the deeper depths. So we did the comparison. This bar chart shows you for the 1.5, 10, and 20 meter wide foundation, how the advanced testing technologies can give you lower settlement estimates, which match well with the footing load test estimates. So with this, I would like to conclude. In situ testing and use of advanced testing technologies is becoming increasingly more important than the conventional boreholes and laboratory testing to generate realistic and site-specific results. Cone penetration test with piezo cone digital data acquisition is now gradually becoming popular and is being used on several important projects. And this is driven by advanced data acquisition and sophisticated. Authors hope, we hope that the CPTU testing will soon evolve in the country for routine soil investigation and characterization to assess the geotechnical parameters. With better understanding of the technology and increased use of geotechnical investigations, geotechnical engineers can ensure a reliable and economic foundation design. Just for your information, Bureau of Indian Standards has recognized the importance of CPTU and is currently formulating a code of practice for this test. SPT energy measurement is also being introduced in the IS code, IS 2131 for the first time. And the draft code is under circulation. So we hope that with the use of these technologies, there will be a big revolution in the foundation design and a lot of saving in the foundation. Thank you very much. I hope I have been within the time allotted. Uh, I'm really grateful to uh, Professor Bablu and Professor Amit, and also University of Waterloo team for giving me this opportunity to make this presentation. Thank you.
Thank you very much, sir. You have been very on time. And also we are very much thankful for your nice presentation, and especially when you link the theoretical study, practical aspects, and then their implementation in the field, because you are directly linked with the field studies, or your studies are directly related to the field work. So that is very nice to see that. And especially you talked about the advanced testing facilities that you have, and then using that you are able to save crores of money. And obviously the initial cost of this advanced testing is high, but then if you see in the long term, definitely 3600% saving, that is huge. So
You see,
uh,
spending 45 lakhs to
yeah,
save
55 lakhs initial
16
investment, but
crores
yeah,
is huge.
yeah, it's
It's
huge.
worth
It's
the
huge.
investment.
Yeah, it's huge. But then the only issue is that the company like you who can afford this kind of testing facilities, can it be afforded by the contractor or local
No, you will
users
be
who can?
surprised that it is not that expensive. It's a
Okay,
matter of, coming forward to do it. Hmm.
okay, yeah, and and also the technical expertise, because these advanced
Oh,
testing
yes.
requires technical expertise and special training. So I'm sure that your company also gets involved in training the students to do these advanced testing.
Training
Uh,
of students, we have not been involved yet. But yes, that would be an interesting option. Um,
yes, because I think because you have got so many good facilities that you can yourself start a training institute and then start giving the training to students, so that they are actually aware of, because major issue is the awareness about the testing facilities that are available, and then how to use that, and then how to interpretation is very important.
oh,
I've
yes.
seen many students, they do the lab testing, they get the data, but they don't know how to do the interpretation and extract the information that is required. So very nice presentation, sir, and I'm
So you
sure that
have to be a complete geotechnical engineer to be able to get the benefit of geotechnical data.
yes, correct. So completely involved, and I'm sure that the participants who are here must have been benefited listening to you, and then hearing you, such a great personality. I think only few figures are there in India who can uh, who has reached to your level. So
Very
uh,
kind of you to
I
say
have
that.
been admiring you since when I came in contact with you, and then I still admire you. So,
Thank you.
Dr. Bablu, would you like to add something? He was just here, and then he's also facing some technical issues related to internet. So, thank you very much, sir. Once again, I think it's a
Most
lunch
welcome.
time for you, so we'll not stop you from your lunch, and we'll move forward for the next keynote speech uh, that is scheduled. We are waiting for Duncan to join from UK. So he has agreed to participate. He has also given consent to TC206 to be the organizing partner of this event. So by the time, Dr. Bablu, you can also add something.
Yeah, thank you. Yeah. No. I'm waiting actually. In between, I am in my home, so some network connectivity issue is there. I heartily thankful on behalf of the whole organizing committee to Dr. Ravi Sundaram sir. He kindly agreed with a very short duration, and it's a
Duncan has
very
joined.
wonderful, insightful presentation. Useful not only for the student, but for young researcher like us also. the field experience you have shared, the new equipment, new testing facility, and most of them, nowadays we are talking about the energy, SPT and all. So based on that, it is very nice to hear that BIS is going to be implemented considering in the code helper vision, and that is really nice. So I really very much thankful to you, sir. And I can see the participation number raised more than 70. So that shows the sir quality and interest in your presentation. So quickly, I will just check. One question is coming. How does a CPT test determine the effects of groundwater table on the SBC calculated? Can it be performed using empirical equations?
To determine the groundwater level from the CPT, normally what we would do is we would conduct a dissipation test below the CPT. The dissipation test is, when you push the cone, you measure the pore water pressure. Basically, it is the hydraulic head above the level at which you are doing. So you hold the test at that level, and with time that pore water pressure will dissipate. And uh, from that you can get the time required for the dissipation, and you would know how much is that additional pressure which is required. So from that you can actually get a very good estimate of what the groundwater level is. The CPT software itself has a built-in system by which you can estimate the pore water pressure, the groundwater table. And once you have the groundwater table, then you can use it in all your analysis the way you want.
Great, sir. I can see Duncan has joined. So
Can you hear me? I'm just
yeah,
checking.
we can hear you, sir, and we can also see you.
So thank you,
if-
Dr. Ravi, sir. Very nice presentation.
So thank you,
Have a
everybody,
nice
and
day.
welcome, Dr. Duncan. I look forward to your presentation.